Have you ever looked closely at a photograph of a satellite, a lunar lander, or the James Webb Space Telescope, and wondered why so much of it is wrapped in shimmering gold foil, like a billion-dollar piece of engineering was hastily gift-wrapped before launch? It looks almost too simple, too cheap, too much like kitchen aluminum foil to belong on a machine that cost more than most countries spend on their entire space programs in a decade. But that gold covering is not decoration, and it is not an accident. It is one of the most quietly brilliant survival tools ever engineered by human hands, and understanding why it exists will change the way you look at every spacecraft photograph for the rest of your life. Space is not simply cold. That is the first myth we need to destroy before anything else makes sense. Most people imagine space as an endless freezing void, and in a sense that is true, but the reality is far stranger and far more dangerous than a single temperature. Space is a vacuum, and a vacuum behaves nothing like the environments we evolved to survive in on Earth. Here on the ground, heat moves in three ways. It conducts through solid materials, it convects through moving air or water, and it radiates as invisible electromagnetic waves. Out in the vacuum of space, two of those three mechanisms simply vanish. There is no air to convect heat away, and without a surrounding atmosphere to touch, conduction only matters between parts of the spacecraft itself. That leaves radiation as the only way heat can enter or leave an object floating in orbit or drifting through interplanetary space. And radiation is a far less forgiving mechanism than most people realize. Picture a spacecraft orbiting Earth. On the side facing the sun, unfiltered solar radiation slams into the surface with an intensity that can push temperatures above 250 degrees Fahrenheit, hot enough to warp metal, melt sensitive electronics, and destroy delicate optical instruments in minutes. Meanwhile, the exact same object, on the side facing away from the sun and toward the blackness of deep space, temperatures can plunge below negative 250 degrees Fahrenheit, cold enough to make most materials brittle, crack seals, and freeze lubricants solid. This is not a gradual temperature change like a chilly morning turning into a warm afternoon. A spacecraft in low Earth orbit crosses from blistering sunlight into pitch darkness roughly every 45 minutes, meaning it experiences this violent temperature swing of nearly 500 degrees over and over, 16 times a day, for its entire operational life. No human structure on Earth is ever asked to survive that kind of relentless thermal violence, and yet spacecraft engineers have to design hardware that not only survives it, but keeps functioning perfectly through every single cycle. This is the problem that gold foil, or more precisely gold-colored thermal blanketing, was invented to solve. Engineers needed a way to control how much radiant heat a spacecraft absorbs from the sun and how much heat it loses to the freezing blackness of space. And they needed to do it without adding enormous amounts of mass, because every single kilogram launched into orbit costs an enormous amount of money and rocket fuel. The solution that emerged from decades of aerospace research is called multi-layer insulation, and it is one of the unsung heroes of spaceflight engineering. Multi-layer insulation, often shortened to the acronym MLI in engineering circles, is not actually made of solid gold. This surprises almost everyone the first time they learn it. What you are seeing in those famous photographs is usually a thin polymer film called Captain, developed originally by DuPont, coated with an extremely thin vapor-deposited layer of aluminum, or in some specific applications, genuine gold. Captain itself has a naturally amber, honey-colored appearance, and when light reflects off its metallized surface, the combination produces that unmistakable warm golden shimmer that has become one of the most recognizable visual signatures of space hardware. So in many cases, what looks like gold is actually a brilliant piece of material science, using cheaper and lighter materials to achieve a gold-like appearance and gold-like performance. But here is the crucial detail that most casual explanations get wrong or skip entirely. In certain specific and carefully chosen applications, spacecraft engineers use genuinely real gold, and they do it for reasons that have nothing to do with looking impressive. Gold possesses a set of physical properties that make it almost irreplaceable for certain jobs in the harsh environment of space. And once you understand those properties, the choice stops looking like an indulgence and starts looking like the only rational engineering decision available. The first property is reflectivity in the infrared spectrum. Most of the punishing heat that threatens a spacecraft does not arrive as visible light. It arrives as infrared radiation, the same invisible wavelength your body gives off as warmth, and the same wavelength a thermal camera detects. Gold happens to be one of the most efficient reflectors of infrared radiation known to material science, reflecting somewhere between 95 and 99% of infrared wavelengths that strike it. This means a gold-coated surface can bounce away almost all of the incoming thermal radiation from the sun before it ever has a chance to heat the spacecraft's internal structure. At the same time, that same reflective property works in reverse, trapping the small amount of heat generated by the spacecraft's own internal electronics and preventing it from radiating away too quickly into the cold of space. Gold effectively acts as a two-way thermal mirror, keeping the outside heat out and the inside heat in, which is exactly what a machine needs when it is being cooked on one side and frozen on the other simultaneously. The second property is corrosion resistance, and this one matters more than people expect. Unlike aluminum, silver, or copper, gold does not oxidize or corrode when exposed to atomic oxygen, ultraviolet radiation, or the extreme vacuum conditions found in orbit. Many spacecraft in low Earth orbit are bombarded by atomic oxygen, a highly reactive form of oxygen created when the thin residual atmosphere is split apart by solar ultraviolet radiation. Atomic oxygen is corrosive enough to eat through many common metals and polymers over months and years of exposure, slowly degrading a spacecraft's protective surfaces. Gold simply does not react to this bombardment in any meaningful way, which means a gold-coated surface applied before launch will still be performing exactly as designed years or even decades later, without a single maintenance visit. Because obviously, nobody is available to send a repair technician to a satellite orbiting hundreds of miles above the ground. The third property is exceptional malleability and ductility. Gold can be hammered or vapor deposited into layers only a few millionths of an inch thick, while still maintaining a continuous, defect-free reflective surface. This matters enormously in an industry where every gram of mass has a direct and painful cost. A gold coating thin enough to be measured in microns can provide the same reflective performance as a much thicker layer of a lesser material, which means engineers get world-class thermal protection without paying a brutal mass penalty. In fact, because the coatings used are so incredibly thin, the actual amount of gold used on a typical spacecraft component is startlingly small, often just a few grams spread across an entire surface, making the material cost trivial compared to almost every other component on the vehicle. The fourth property, and one that is often overlooked, is gold's outstanding electrical conductivity combined with its resistance to tarnishing. Spacecraft rely on thousands of tiny electrical connectors, and in the vacuum of space, connector reliability cannot be compromised, because a single failed connection could end a mission worth hundreds of millions of dollars. Most metals used for connectors will eventually oxidize or develop resistance, causing corrosion over time, even in supposedly clean environments. Gold-plated connectors resist this degradation almost completely, ensuring that electrical signals travel cleanly and reliably for the entire lifespan of the mission, whether that mission lasts 18 months or, as we have seen with certain deep space probes, more than 4 decades. Now let's talk about where you can actually find real gold being used on real spacecraft, because the examples are more fascinating than most people expect. The Apollo lunar module, the spidery-looking vehicle that carried astronauts down to the surface of the moon, was wrapped extensively in gold-colored multi-layer insulation to protect its delicate systems from the moon's own brutal thermal extremes, where surface temperatures swing from scorching daytime highs to devastating nighttime lows with no atmosphere whatsoever to moderate the transition. Astronauts and engineers alike referred to the material informally as gold foil, and the name stuck in public imagination ever since, even though much of it was aluminized Captain rather than pure gold. The James Webb Space Telescope offers perhaps the most stunning and precise application of true gold in the history of spaceflight. Each of its 18 hexagonal primary mirror segments is coated with an incredibly thin layer of pure gold, roughly 100 nanometers thick, a layer so thin that if you could somehow collect all the gold used across the entire telescope's mirror array, it would weigh less than a single golf ball. Why gold for a telescope mirror? Because Webb was built to observe the universe in infrared light, peering through cosmic dust to see the earliest galaxies and the faintest, coldest objects in existence. And gold reflects infrared light more efficiently than almost any other material available, achieving over 98% reflectivity in the infrared wavelengths Webb was designed to capture. Without that gold coating, the telescope simply could not achieve the extraordinary sensitivity that has allowed it to photograph galaxies formed within a few 100 million years of the beginning of the universe itself. Communications satellites orbiting thousands of miles above Earth also rely heavily on gold-coated components, particularly in their antenna systems and waveguides, where signal integrity depends on minimizing electrical resistance and preventing any form of surface degradation over a working lifespan that can stretch beyond 15 years without any possibility of repair. The International Space Station, a sprawling structure assembled piece by piece in orbit since the late 1990s, is wrapped in extensive multi-layer insulation blankets across its modules, protecting the pressurized compartments where astronauts live and work from the same violent day-night temperature swings that threat every object in low Earth orbit. Mars rovers, including Curiosity and Perseverance, carry gold-colored thermal blanketing wrapped around sensitive electronics bays to survive the Martian day-night cycle, where temperatures can swing more than 100 degrees Fahrenheit between a sunny afternoon and a frigid Martian night, all while operating in an atmosphere far too thin to provide any meaningful thermal buffering. It is worth pausing here to appreciate the layered construction of a typical multi-layer insulation blanket, because it is far more sophisticated than a single sheet of shiny material. A real MLI blanket is often built from 10, 20, or even more individual layers, each one a wafer-thin sheet of aluminized or gold-coated polyimide film, separated from its neighbors by a fine mesh or netting material designed specifically to prevent the layers from touching each other. This separation is not a minor manufacturing detail. It is the entire secret to how the blanket works. If the reflective layers touched each other directly, heat would conduct straight through the stack like a chain of falling dominoes, defeating the entire purpose of the design. By keeping a tiny vacuum gap between each layer, engineers force heat to travel only through radiation, bouncing back and forth between reflective surfaces, losing a significant percentage of its energy at each bounce, until only a small fraction of the original heat ever makes it through to the other side. 10 or 20 layers of this bouncing effect can reduce heat transfer by well over 90% compared to a bare, unprotected surface, all while adding remarkably little weight to the finished spacecraft. The engineering discipline required to design and install these blankets correctly is immense. Every seam, every cutout for an antenna or a sensor, every fold around an awkwardly shaped component has to be carefully tailored, because even a small gap in the coverage can create what engineers grimly call a thermal short, a tiny weak point where heat sneaks through and potentially damages a critical component. NASA and other space agencies have entire specialized teams dedicated purely to thermal blanket design, testing prototypes in giant vacuum chambers that simulate the brutal thermal cycling of orbit long before any hardware is cleared for an actual launch. It is also worth addressing why engineers do not simply use thicker traditional insulation, the kind you might find lining the walls of a house, or why they don't use active cooling systems for everything. The answer again comes back to weight and power. Every kilogram sent into orbit requires enormous amounts of rocket fuel to accelerate, meaning mass is arguably the single most expensive resource in all of spaceflight engineering. Traditional bulk insulation materials are simply too heavy for the level of protection they provide compared to the feather-light performance of multi-layer insulation. Active cooling systems, meanwhile, require power, moving parts, and additional complexity, all of which introduce more potential failure points into a system that, once launched, often cannot be repaired by human hands. Passive thermal protection like gold-coated MLI blankets requires no power, no moving parts, and virtually no maintenance, making it one of the most elegant and reliable solutions available to spacecraft designers, which is exactly why it has remained a standard feature of spacecraft design for well over half a century, from the earliest Mercury and Gemini era hardware all the way through to the most advanced telescopes and interplanetary probes flying today. There is something almost poetic about the fact that one of humanity's most ancient and treasured materials, prized since the earliest civilizations for its beauty and rarity, turned out to be one of the most perfectly suited substances for surviving the harshest environment our species has ever tried to conquer. Gold was mined from the earth for thousands of years to decorate the tombs of pharaohs and the crowns of kings, and now impossibly thin traces of that same element are helping robotic explorers survive on the surface of Mars and helping a telescope peer back toward the very beginning of time itself. That golden shimmer wrapped around a spacecraft is not vanity. It is one of the purest expressions of applied physics you will ever see, a direct answer to one of the most unforgiving engineering problems in existence, hiding in plain sight inside a material humans have treasured since the dawn of civilization. So the next time you see a photograph of a satellite, a lunar lander, or a deep space telescope wrapped in that unmistakable golden foil, you will know exactly what you are looking at. You are looking at a carefully engineered thermal shield, built from ultra-thin reflective films, sometimes genuine gold and often gold-colored polyimide, designed to bounce away punishing solar radiation, trap precious internal heat, resist corrosive atomic oxygen, and keep sensitive electronics alive through temperature swings that would destroy almost anything built for use on the surface of our own planet. It is quiet, unglamorous, and almost invisible in terms of public attention. Yet without it, almost nothing we currently know about the universe beyond our atmosphere would have ever been discovered. If this deep dive into the hidden engineering of spaceflight expanded the way you see the cosmos, make sure you are subscribed, because there are countless more stories like this one waiting to be uncovered, hidden in the smallest details of humanity's greatest machines.